Jupiter holds 318 Earth masses, more material than every other planet in the solar system combined, yet most of that weight is the lightest gas. How did Jupiter become massive enough to take the solar system's hydrogen and helium, while the inner planets stayed small and rocky? Jupiter did not begin as a finished world. The established picture starts with a young sun surrounded by a protoplanetary disk, a broad rotating sheet of hydrogen, helium, dust, rock, metal, and ice. The gas made up most of the disk's mass. The solids were a minority, but they mattered because planets need seeds. Dust grains stuck into larger grains. Larger grains became pebbles. In places where enough solid material concentrated, kilometer-scale planetesimals could form. The inner solar system was hot. Close to the sun, water stayed mostly as vapor. Rock and metal could survive there, but ice could not remain as solid building material. Farther out, beyond the frost line, water ice could persist. That single temperature boundary changed the amount of solid material available to growing worlds. Beyond the frost line, a forming planet did not have to build only from rock and metal. It could also collect ice-rich solids. That gave the outer disk a larger supply of planet-building material per orbit than the hotter inner disk. Models of early planet formation support the idea that the region near the water snow line helped concentrate solids and form early planetesimals during the gas-rich phase. This does not mean the frost line alone made Jupiter. It means Jupiter formed in the part of the disk where a large core had a better chance to grow quickly. A core is the heavy central part of a giant planet. Rock, metal, ice, and other elements heavier than hydrogen and helium. For a gas giant, the core matters because gravity has to become strong enough to hold a thick atmosphere while the nebula still exists. The problem is no longer why Jupiter is large today. The problem is how it crossed the threshold while the gas disk was still present. Core-accretion models treat giant planets as two-stage objects. First, a solid core grows. Then, if that core becomes massive enough, it pulls in hydrogen and helium from the surrounding nebula. Roughly 10 Earth masses is often used as the scale at which a rocky and icy core can begin serious gas capture, although the exact threshold depends on temperature, opacity, and how solids keep arriving. This stage is a race. Building the core is comparatively slow. Simulations of gas accretion onto protoplanets find that once the conditions are right, the gas capturing phase can be much faster, with growth timescales around 100,000 years in some models. Other simulations of a Jupiter-mass planet in a disk find even shorter nominal mass doubling times, though those rates depend on numerical assumptions. The supported picture is therefore not that Jupiter slowly gathered gas for the whole history of the solar system. It is that a core formed early enough, then gas capture accelerated while there was still gas to capture. The nebula did not wait. Young stars heat their disks with radiation, and their outflows push material away. Over time, the gas thins, escapes, or falls onto the star. Once that gas is gone from a region, no nearby planet can become a new Jupiter there. Meteorite magnetism gives one way to time this disappearance. Some ancient carbonaceous chondrites preserve magnetic records interpreted as evidence for nebular magnetic fields, which require gas in the disk. Those measurements are used to constrain the lifetime and possible two-stage fading of the solar nebula. The exact timing is still debated, but the consequence is firm. Gas giants have a deadline. Rocky planets do not need nebular hydrogen and helium to exist, so the inner planets could keep assembling from solids after the gas supply had largely disappeared. They stayed small in mass because they never crossed the same gas capture threshold while the reservoir was open. Jupiter's present interior is the evidence left behind by that early race, but it is difficult evidence. No instrument has seen a sharp core directly. The planet hides its deep structure under thousands of kilometers of hydrogen and helium. Juno helps by measuring Jupiter's gravity field as the spacecraft passes over the planet. Tiny changes in the spacecraft's motion reveal how mass is distributed inside Jupiter. Juno also measures the atmosphere and magnetic environment, adding constraints on the planet's deep layers. Those measurements do not give a single clean answer. Interior models using Juno gravity data support a dilute core, with heavy elements spread through a deep region rather than packed into one simple ball. Estimates from those models include about 7 to 25 Earth masses of heavy elements in the dilute core. Earlier hydrogen-helium calculations implied a more compact central core of about 14 to 18 Earth masses, while other interior reviews allowed an even broader range. The evidence supports core accretion as a strong explanation for Jupiter. It does not yet settle the exact structure of the core or the precise path Jupiter took to reach its mass. Jupiter's composition creates a tempting comparison. The planet is made mostly of hydrogen and helium, the same two elements that dominate the Sun. In that limited sense, Jupiter is star-like, but Jupiter was never close to becoming a star. Sustained hydrogen fusion requires far more mass than Jupiter has. A common boundary for the smallest true stars is around 80 Jupiter masses, depending on composition. Even brown dwarfs, which confused deuterium for a time, are usually placed above about 13 Jupiter masses. Jupiter has 1 Jupiter mass. So the important comparison is not a failed sun. It is a planet that captured the disk's gas before the disk was removed. Its composition records the nebula. Its mass records the timing. Jupiter became the solar system's giant because it appears to have won an early race that the inner planets could not enter in the same way. Beyond the frost line, more solid material was available. A large core could form, while the young solar system still contained nebular hydrogen and helium. Once that core became massive enough, gas accretion could proceed quickly enough to build a planet larger than all the others combined. When the young sun's radiation and wind cleared the remaining gas, the outcome hardened. No new gas giant could form nearby without a gas reservoir. The inner planets were left to grow mainly from rock and metal, and they became small, dense worlds instead of hydrogen-helium giants. The answer is therefore timing joined to location. Jupiter formed early enough and far enough from the Sun to build a massive core and capture gas before the nebula vanished. What remains open is the fine print inside the planet. How compact or diluted its core is, how its heavy elements are distributed, and which exact formation route produced the Jupiter that Juno is still weighing today. That's Y-Source. If this was worth your time, like it, share it, and tell me in the comments what you want examined next. If you would like to support this work, the Patreon link is in the description.